mailing list that we have in the lab. Most of you will be on it always, the quantum announcements list. Some of you will not be on this list, but if you would like to be, just drop me a message. And actually Jamie is doing this, but I'll forward this to him, and then you will end up on this list and hear all this splendid stuff going on. Okay, today I want to finish talking about function analysis. So we'll see a tiny little bit about representation of C-star algebras. That's basically mentioning just the central result there. And then I'll say a few things about phenomenon algebras. And I thought it would be good to actually define the spectral presheaf after that, which is kind of the central object in the Topos approach. And we can define this now that we've seen the function analysis, the true significance of this object, and in certain aspects of it will become clear later when we talked about Topos theory a bit more, but probably it's not a good idea to do another 2 sessions just technical definitions before we define this thing. So I thought it might be good to define it today. Last thing we did last time was Gelfand duality, so basically saying there is equivalence between 2 categories. So the one category was abelian C-star algebras, and the others is compact Hausdorff spaces. And how do we get from one to the other? Well, you go here, take an abelian C-star algebra, and you get its spectrum. So this could call it signal this function. The other way, you take a compact Hausdorff space and just look at the continuous complex valued functions. So let's write it. Maybe this. Okay, this is another pen. I forgot to bring my own. What it basically says is every abelian C-star algebra can be represented as continuous functions on a given compact Hausdorff space. And compact Hausdorff space is the spectrum of the algebra. And we'll be using this a lot actually. So what about representations of general C-star algebras? Of course, general C-star algebras are not necessarily abelian, and there's another very important representation theorem for them. And let's first say what a representation is. Representation of a C-star A is simply homomorphism from a bounded operators in some Hilbert space. And if, let's give this a name, let's call it phi. If your phi is injective, then the representation is called faithful. So and the theorem then says this needs some work actually. This is the following. Theorem also by Gelfand. Could be different ways of writing that name. Actually, I think I used writing with AI. Sometimes you find my mark written with EU instead, but it's not very important. Also, C was attached to this. The theorem says every C-star algebra has a faithful representation. So this of course means that we can always think of C-star algebras as being operators on some Hilbert space. Sometimes this isn't the best way, but it's always possible. You can always represent your algebra faithfully on some Hilbert space, and actually in the proof of the theorem, the Hilbert space is constructed very explicitly. So it's this construction of the Hilbert space is the name itself. That's called GNS construction. GNS. So I just mentioned this here. This is something you can find in many books, and it's a beautiful construction. Okay. This is all I want to say about C-star algebras. Obviously there's much more to be said, but we won't need more. Next thing I want to talk about are for Norman algebras, and actually those are technically more important in what we're doing in the Topos approach. And the main reason is that they have lots of projections, and in which sense they have many projections will become clearer. Again, this is a phenomenon, this distinction between C-star and for Norman algebras that you would not see in finite dimensions, but in infinite dimensions you can see a difference. And the reason is, if your Hilbert space is infinite dimensional, there are different interesting topologies on B of H, while in finite dimensions they don't coincide, and this is why I don't see a difference. We had one topology already, which was the norm topology. So every operator has a norm, these are bound operators on a finite norm, and we can talk about convergence in the norm, and we saw at least implicitly that C-star algebras are closed in the norm topology. And this has a lot to do with the C-star property, which links the norm and the star. Another topology is the so-called weak operator topology. And this is also a locally convex topology. And all on the slides I give you a family of semi-norms which define this topology, but we won't really go there. The idea that you can have about it is that this is a weaker topology, so we have less open sets, so intuitively more sequences should converge in this. So you can start from a C-star algebra and complete it and get something bigger. And there's actually a process of doing this. It's called forming the enveloping phenomenon algebra. But I should first say what a phenomenon algebra is. I will be deliberately brief on this. Of course, really understanding what being closed in the norm in the weak topology means is a bit more work. So just say following definition: the C-star algebra, let's call it N, that is closed in weak and also we want explicitly that it contains the identity. One such a C-star algebra is called and then there are several things you can prove about phenomena. First of all, you observe that every phenomenon algebra is a C-star algebra. Very often that's not the best way of thinking about a phenomenon algebra, but all the structures we had in C-star algebras are also there in the phenomenon algebra. And what we have, as I said, are lots of projections. It's the following theorem. set P of n of projections in a, usually write B and A for Norman algebra, is a complete lattice, and moreover it is a distributive lattice if and only if your algebra is abelian. Okay. We talked about projections in E of H, and we saw we can form these arbitrary means, which on the level of subspaces is just in the section of the subspaces, and this gives you another closed subspace, I should say, to be really precise, and you could form arbitrary joints, which was, well, first of all, the linear span of your subspaces and then the closure of that. And a similar thing holds in every phenomenon algebra. In C-star algebras, in contrast, you very often just have the zero projection and the identity and no other projections at all. I mean, of course, as I said, the phenomenon algebra also is a C-star algebra, so there are all kinds of C-star algebras, but typically, if you want many projections, you have to go to rather special C-star algebras. And this is an interesting thing. Distributivity of the lattice was well, this behavior of means over joins. So if you have three projections, P and Q, or this is P and Q, or this is distributivity, and this only holds if your algebra is abelian. That's a pretty important point, actually. So we see that non-commutativity and non-distributivity, they are the same in this sense. Okay, there's a nice algebraic characterization of phenomenon algebras, which uses the so-called commutant, which is just a centralized algebraically. So let's define this. It's then we pick a certain family of operators. I should maybe say that whenever I talk about a phenomenon algebra, I actually think of it as being represented by operators on some real space. So we can always do this by this theorem, and implicitly I'm always using this. There is an abstract notion called a W-star algebra, which is representation free, if you like, but I will not go there. So we pick some family of operators, and then commutant with f prime of f is well, the following. This set of all operators B in B of H such that for all operators A in my family F, I have AB minus BA, which is this commutator AB is 0. So I look for all those operators which commute with every operator in my family. Let's pick an example. If we pick F is the whole of U of H, then F prime is just a multiple, so the identity operator. It's the only operator is commuting with everything you have. Likewise, if I writing this as f, yet this as f prime. Well, these are the trivial examples, but this gives some idea. I suppose I shouldn't write over here, or?
Yeah, probably.
Okay. So. So a theorem which actually is by von Neumann is the following. It's called the double theorem, and it says if A is self-adjoint. I didn't say before what self-adjoint algebra means. It means for every operator you also have the adjoint contained in it. The self-adjoint algebra of operators on Hilbert space H, and also we want that the unit element is contained. Then the weak closure of A. This is nothing but the von Neumann algebra that you obtain from this algebra A. This coincides with a double prime, taking the coetant twice. This means, of course, in particular, n equals n double prime for every von Neumann algebra. We will be using this sometimes for example, even if we don't start from an algebra, we start just from a set of operators which is self-adjoint, so with every operator contains its adjoint. And we generate a von Neumann algebra from it by just applying this double commutative construction. If we have that f be set only in this case of operators on page, but we also assume that it contains the identity, because we always want that the identity is in our von Neumann algebra. That if we subjoin containing 1, then f is called VNA generated by f. Example, this is the one actually we're using, is take f to be the set. Well, just take a single projection P and take the identity, then f double prime is, well, all complex multiples of P plus all complex multiples of the identity. Which of course generates you things like 0, which generates you minus p, all these things. So these are the smallest non-trivial von Neumann algebras that you can have at all. The trivial one is just this guy, just the multiples of the identity, but the smallest non-trivial ones are of this form, and they show up sometimes later on. Okay.
Andreas, quick question about the theorem, just to clarify things.
Yeah.
So self-adjoint means that there is a star operation, and it's closed with respect to this star, self-adjoint algebra, right? So when we take the big closure of this, then this thing becomes a sister algebra, I guess, right? The norm has a sister property, and so it becomes a Feynman algebra or something?
If we take the weak closure,
Yeah.
we actually get a phenomenon algebra, because by definition phenomenon algebras are those which are weakly closed.
Right. So, okay.
We do not assume here, we don't have to assume that we start from a C-star algebra.
But it becomes a sister algebra.
It becomes a C-star algebra automatically because the weak topology is weaker, and hence it is also non-closed.
Okay.
Yeah.
Did that have to be projected down there? Any
yes.
self-adjoint operator?
Well, it actually, you will see why. It will have to be a projector when I say this is the smallest non-trivial one. The reason is the spectral theorem. If you have some other operator in there, then, well, let's for simplicity assume you have some self-adjoint operator in there, then via the spectral theorem you will see that you have all the spectral projections also in the phenomenon algebra. So you will have more than here. If you have an arbitrary operator, you decompose it into A1 plus I times A2, where A1 and A2 are self-adjoint, and then a similar argument applies. So this is why actually the smallest phenomenon algebras are this form where P is a projection. Okay. Yeah, then we get something interesting when we look at abelian phenomenon algebras, and since they are C-star algebras, they have the Gelfand spectrum. Now, when you think about it, you see that you have these projections contained in there, and the projection has spectrum just 0, 1. The Gelfand duality says, okay, every operator becomes a continuous function on the Gelfand spectrum. Now you have functions which are just taking two values, so they're characteristic functions of some subset of the Gelfand spectrum. If you want such a function which obviously jumps, you want this to be continuous, you have to pick a pretty wild topology on your spectrum to make such a functions continuous. And this is actually what happens. It turns out that the Gelfand spectra of abelian phenomenon algebras are extremely disconnected. So let me define this. A topological space X is extremely, or I was told it's actually better English to say extremely disconnected. You find both conventions, so it seems extremely is the older notion, but extremely is more common in function analysis for some reason. So, already, space is called extremely disconnected if the closure of every open set is open. Let's make this very explicit as well as closed. Well, obviously every discrete space is of that kind, but there are also non-discrete spaces which are of this kind. And it's very hard to get any kind of intuition of how such a space looks like. It's the only continuous curves in such a point sit in such a space sit at a point. Yeah. It's pretty badly disconnected, and I think that's the most extreme condition of disconnectedness apart from discreteness that is imaginable. But these things show up, and so the next theorem, which actually needs quite a bit of proving, is the following: if V is abelian phenomenon algebra, then Gelfand spectrum segment V is I use this slightly unusual letter V for abelian phenomenon because someone, Chris and I, came up with this convention for ourselves very early on, and we always kept it that way. It's more common in literature that we talk about abelian algebras to have this A, but there are lots of conventions. So just because it fits in with what you find if you read the papers on the Topos approach, I'll stick with this convention. So whenever something's called V or V prime or something like this, it's an abelian phenomenon algebra. And phenomenon algebras actually are written as curly N, which is also what's sometimes used. Most people use curly R for some reason, but this could cause confusion with other notions we have in the Topos approach, so we change to N. It's like 1, 1, 1. Okay. Well, I don't think this was the initial intention. Okay. Now, another thing that we need to know about the Gelfand spectra of abelian C-star algebras is the following. So, first of all, you get the idea that in an extremely disconnected space, you have lots of sets which are closed and open at the same time, because you can take an open set, take the closure of it, and you get something which is closed and open at the same time. By the way, the complement of a closed set is also closed, obviously. And one can prove the following. So first of all, V is a phenomenon algebra, so we already know that the projections in V form complete, actually distributive lattice, because it's an abelian phenomenon algebra. There is another lattice relating to this topology directly, which is isomorphic to the projections in V. And this is the lattice of Klopen subsets. Klopen means closed and open at the same time.
This related to Stone's representation theorem.
Yes. Yes, it's very much related to that. Something I should have written down a while ago. This must be known, I should have put it on the slides. What we're basically talking about is Stone duality for the complete Boolean algebra of projections in V. And the space you get, a Stone space, should be, a bit carefully because I haven't checked it, but it should be homomorphic to a Gelfand spectrum of the algebra. This should actually be well known. So let's first define this awful word Klopen, but it's better than always writing closed open or something like this. So set S is called Klopen if it is closed and open. Okay. And there's some, well, I find quite some cases actually. You can get the German equivalents of these words. So closed is geschlossen and open is offen. There was a suggestion of calling these sets geschlossen, which never really took hold. It sounds extremely funny if you know German. Okay, so I'm not even writing it down. So this other lattice is lattice of Klopen subset. So I didn't actually define this lattice yet, but what would you do? I mean, if you have a family of Klopen subsets, how would you define the join? You can't just take the set theoretic union, because, okay, you still get something which is open, but need not be closed in general. So you define, you have such Klopen subsets as I define a join to be, well, the closure of the union, so set theoretic union. And similarly, you define the meet as the interior of the intersection, because the intersection surely is closed, but it need not be open. And then you can see easily the interior of every closed set is closed in this topology. Just like the closure of every open set is open. So you see this. So this is why this also becomes a Klopen set. This is how you can define a lattice structure. So gives lattice, let's write it, CL of sigma V of Klopen subsets, and we also have an auto-complement. As I said, the complement of every Klopen set is Klopen, so you can actually just take the set theoretic complement and maybe not send it to the auto-complement here. So complement is set theoretic complement. Now the theorem says this lattice is isomorphic to the lattice of projections. I'll show you the isomorphism. And it's not very surprising once you've seen it. So, well, basically I said everything. P, which of course the projections of V is isomorphic to CL sigma V. I write explicitly they are isomorphic as lattices, as complete lattices. Proof is just giving you isomorphism. So alpha goes from projections to the Klopen subsets. Take projection P and you send it to all those lambda in sigma V, such that lambda applied to P equals 1. Remember we looked at lambda applied to P already. These are multiplicative linear functionals, which in particular means, well, let's write down again, I think it's useful. So lambda of P is lambda of P squared, because this is a projection. This is lambda of P squared, which of course just means we have either 0 or 1. And we just pick those which are sent to 1. This is very closely related actually to taking the Gelfand transform of P. I take the Gelfand transform of P, as I said, I get a function which for some lambdas is 0 and for others is 1. And here I just pick those for which it is 1. The Gelfand transform of P is just a characteristic function of this subset, and let's call this, for later reference, S index P. That's the Klopen subset I construct from P. Basically, this is the Gelfand transform of P. And this also tells you how you can get back. You take the characteristic function of this subset and take the inverse Gelfand transform, you get back your projection. So these are the ways you can go back and forth. Also for later reference, it is interesting at this point. These guys here, they are very specific to the Boolean subalgebra. So these are actual subset of the Gelfand spectrum, and if you are at V, you just see these. This projection lattice can usually do this, be seen as part of a larger structure, because we will see V as an abelian subalgebra of a bigger non-abelian algebra. So we will typically have V is contained in some n abelian, non-abelian. Then of course we have projections in V are contained in projections of n. In this sense, these guys get a global meaning in the non-abelian algebra, which these sets don't have. But well, because they are actually specific to V. We'll be using this a lot because we will look at projections which lie in different V's. So not just in one, but they lie in different V's. So this gives you relations across different abelian subalgebras. You couldn't see it on this level, but you can see it here. We'll actually see it when I define the spectral presheaf. Okay. Last thing I want to do is the spectral theorem, which is arguably the most important theorem if you want to understand quantum theory. Even if it takes 5 more minutes, I want to start with the simple finite dimensional situation. And I'll be very brief about this, but I want to rewrite what we have in the finite dimensional situation so that you can see much more easily what happens in infinite dimensions. So if we have a self-adjoint operator on a finite dimensional Hilbert space, we know we can diagonalize this guy. And we can write it, actually that's something you can directly infer from the fact that you have a diagonal form. You can write it in the following form. So, H, we have A as self-adjoint, and we have A is sum minus 1 to n, where n obviously is the dimension of the Hilbert space, A by P I for a bunch of pairwise orthogonal projections onto one-dimensional subspaces. These AI are nothing but the eigenvalues. So some of them can coincide, so we may have a degenerate operator, but that's not a problem in itself. So that's the usual thing, and we all know this, and this is basically the spectral theorem in finite dimensions. So there's not much to prove. One important thing is it may happen that one of these eigenvalues is 0. And of course you could rightfully say, let's drop this from the sum because it doesn't contribute. I want to keep it for the reason that I want that these projections Pi sum to the identity. So I explicitly want to include projection onto the eigenspace of the eigenvalue 0 if it's there. So let's write this down by convention include. It doesn't actually play a role in this sum, but it plays a role in how if I just would drop the projection onto the eigenspace for eigenvalue 0, they wouldn't sum to 1 projections. Include 0 such that the sum of these is the identity of. Okay. As I said, I just want to rewrite this very slightly. I define sum over I equals, let me be careful, let me start to count at 1 goes to n ei. So ei sums the first I of these projections onto eigenspaces. Okay, and then first thing we see is En is the identity by this, and our A can be written as sum over I equals 1 to n I minus I minus 1.
Andreas, is that right, the EI? You should be summing up
No,
to
this
I.
is not right. Sorry. I must. Sorry, this is
Different dummy variable.
I must count from j equals 1 to I. Sorry. No, it's perfectly right. Of course. I just want to sum the first I of these, as I said. But then, if you do it this way, this should become correct. And I need a definition for E0 because this starts to count at 1. So I have to subtract E0 at one point. I'm doing this because now well, if I would be talking to physicists, I would just say, okay, we take the infinite dimensions, the sum becomes an integral, and it's all clear. That's basically what happens, but this form is much closer to an integral already because you have the difference in here, and you can imagine that you take a finer and finer partition, as we'll see in a minute, and this is why I wanted to rewrite it this way. So I'll now formulate the spectral theorem. Also, this family of projections that we have here, these EI, they are interesting. So they start at 0. Let's give it a head because this is actually 0 projection. With this index, it grows. You get bigger and bigger projections in the sense you just project onto bigger and bigger subspace. Obviously, they all commute with each other. And from some index, at some index n, we get the identity. What we will do now is actually we will replace these discrete indices by a real parameter. So instead of just having 0, 1, 2, 3 up to n, we'll have a real parameter there. And it still makes sense. Adjoint operator on some little space H and V is revealed in full algebra, which contain A. If that's the case, is a family. So ER is a set. We now have a real index R of projections in V, and that's actually the point. These projections all lie in the phenomenon algebra. This one is why I didn't mention this, couldn't have mentioned this for C-star algebras, because in general they just don't have the projection in this holes in phenomenon algebras, such that, well, first thing is ER is zero projection if R is smaller than the norm of, minus the norm of A, that's what we wanted to say. And ER is the identity if R is greater than or equal to. Second condition is, well, this is a growing family of projections, so ER is smaller than or equal to ES if R is smaller than S. The next thing is ER is following this minimum of all ES for S larger than R. And finally, and that's of course the main point, A is an integral from minus norm A to norm of A R d ER. So how is this to be understood? This is kind of symbolic notation here. This is to be understood right over here. The idea is that you find the partition of the real line, that means the power between minus norm A plus norm A. The finite partition, you make an approximation, and you make this partition finer and finer. So you basically are in this situation that's still here. And you get a sequence of operators, and the statement is this sequence converges in norm to the operator A. So D is meant in the sense of norm conversions of approximating sums. Let's make this very explicit. And A is the norm limit of finite linear combinations in the spectrum. And as you finite linear combinations of orthogonal projections of the form ES minus ER. So this is very explicit, but it's really an important theorem. So every self-adjoint operator has this kind of representation, and I can approximate it by this very simple situation that we saw in finite dimensions.
I think this is analogous to the usual theorem that every function of the right type is approximated by multiples of characteristic functions.
This you would usually have for, yes. Yes, it's kind of an analog to that. You can see, since we are in a B said, projections which show up here go to characteristic functions of subsets. They are multiplied by these spectral values here, so you scale them as necessary. So it's very close to this situation, yes.
So it's obviously like molecular integration.
Yes, this is basically one thing I will not, well, I'd say now, but I will not say anything further. This whole setup for nominal algebras is tailor-made for measure theory and integration theory, but in a non-commutative setting. So many people say the theory of the states of nominal algebras is non-commutative integration theory. We have a certain twist on that, if you like, in the Topos approach when we talk about quantum states as measures. This is potentially interesting for this also, but it's actually quite a good intuition. And also this fact that we have this extremely disconnected topology shows it. Just the fact is, you basically make functions which are measurable, you make them continuous. And so you get a vast number of continuous functions, and this is why your topology is so wild. Maybe there are other requirements later on when you want more connected spaces for other purposes, but for now it's just, we want the spectral theorem, we want enough projections, because we need them technically. But there's nothing dogmatic about this, so I would actually like to see something like, start from a C-star algebra, go to the spectrum, which is a compact Hausdorff space, so it is usually not that disconnected, and then whatever we need about projections, get it from the enveloping phenomenon algebra, but still see this as maybe not continuous functions, but still as functions on the spectrum of the C-star algebra. There must be lots of things known also, it just needs a bit of work to dig them out and then to work out how it can apply to our situation. But this should be possible, I think. There are lots of questions related to that. So, I already said the spectral theorem does not hold in general C-star algebras. You obviously need these projections. And there's something else that I want to indicate because we will be using this. It's the following thing. Okay. Let self-adjoint operator. Now, if delta is a Borel, again, Borel measurable subset of real line. Actually, I want to be a bit more specific because I want a Borel subset of the spectrum of A. Of course, I can take any Borel subset of a real line and intersect it with the spectrum and get a Borel subset of the spectrum, but spectrum is P A. Then exists a projection. Let's write it E of delta. And again, this line is in V, that's the main point. Such that lambda of A is in delta for all lambda in, well, take this corresponding global subset E of delta. So let's write this down. Again, this this is the technical thing that you can infer from the spectral theorem and a bit of this measure theory going on. Actually, I should be a bit more precise in existence for. It's actually for those and only those left of us. So, for lambda. So what I'm saying basically is you can pick any Borel subset of your spectrum and you find the corresponding projection in your abelian phenomena algebra. Now, we will be using this a lot. We want to talk in physics about propositions about the values of physical quantities. So you take physical quantity A, and you want to say, let's write this down over here, the physical quantity has a value in a certain set of real numbers. So you want to say my energy has a value between, I don't know, -1 and +5 in suitable units. So we have propositions and they get a symbolic notation. A is, there's not even the proper element sign, it's really symbolic. The point is these propositions are not mathematical at this point. There's something you want to say about the world, so to say. And there's a certain amount of conceptualizing going on. Obviously, you can't get away from this, so you have to say, okay, there's a physical system, it has physical quantities, and they take values in the real numbers. So these are things we accept, at least for the moment. And then, arguably, physics is very much about what can I say about the truth values of such propositions once I have the state of my system given. Of course, the state may change, so the truth values may change. But arguably, this is a very low-level conceptualizing of what we're doing in physics. And then we have to find mathematical representations of these guys in our physical theories. And in standard quantum theory, this is what happens. So here, picking this subset of the spectrum of A is like saying A has a value in this subset delta, and the mathematical representative of this is this projection E delta. So that's what's going on here. This is how standard quantum theory represents such a proposition, and you need the spectral theorem to do this. We will actually see two ways in the Topos approach. One, two ways to represent propositions which are quite different from this, but one of them starts from this. So first takes this thing from physics, which is not mathematics yet, by the spectral theorem to a projection, and then does something with the projection. The other way is more like what we do in classical physics. Maybe it's a good idea to say how we do this in classical physics. First, let me write down in standard quantum theory, A is delta is represented by, let's write here, this projection. And just to use notation that you find in the papers, this is often written as this. There is a reason why there are these square brackets. The point is that usually we have some structure on our physical quantities. Usually they form an algebra. So if you have A in there, you also have 2A in there. You can have certain propositions about A, but they are the the same, they're not distinguishable by any state from proposition about 2a. So let's say a and delta is the same proposition as 2a is in, well, delta shrunk by a factor of 1.5. This means this mapping from propositions to projections is many to 1. Usually I will not take too much care about this. I'll just take a proposition, so I'll take one representative of the equivalence class and talk about the projection, what the proposition corresponding to the projection. If you're really careful, there are lots of different propositions corresponding to the same projection. There's one thing, but before I tell you how we do it in classical physics, there is another important point that we will be using actually. This has to do with the fact that I already said you take a projection operator that lies in many different abelian subalgebras. Let's assume we have two self-adjoint operators. Let's say we have A, and then for simplicity I'll take a finite dimensional situation. So AI, PI, and you have B is J, J. But now assume just pick something, P1 equals Q1. So they are the same projection. Now, you can have a certain proposition about B, namely B has the value B1, but it's represented by the same projection as quite a different proposition, namely one about A, which is A has the value A1. Now it turns out that it's a good idea to identify these two propositions in the sense that it's not a problem that they correspond to the same projection operator. We explicitly want this, actually. There are people in physics, in foundation physics, who tell you that's a wrong idea. They can measure A in some context, in some experimental setup, and you can measure B, which the operator A and the operator B do not need to commute, so you can measure B in some other experimental setup, and there's no reason why you should have anything comparable between these two different experimental setups. I think if you give up on this, you're basically lost. So it's awfully hard to see how to make sense of this. So okay, it's all on video, but still I think it's nonsense. In this sense, contextuality, some people understand the word contextuality in this sense. If you read Bohr, for example, you find hints of this at least. Bohr is never very clear in what he says. But he definitely says you can only talk about a quantum system in terms of an experimental setup, so in your classical terms that you have at your disposal at the time. And if someone else has another experimental setup, then he can say certain things about the quantum system, but there's no clear way how these two things are connected. Mathematically we see, of course, the same projection can show up here, and this gives us a connection. And I think also physically this makes sense. And in this particular sense, what we're doing all the time is non-contextual, because the projection P is important and not the abelian subalgebra in which it lives. It's actually, we'll actually formalize in a minute exactly what different abelian subalgebras have in common, because we look at their projections. So in this sense, we have a non-contextual model. I'd still say we incorporate contextuality and things like this. This word contextuality is understood in many different ways. So this kind of well, just a word of warning and a bit of personal opinion, which you may like or not. Anyway, I'll tell you how we represent such propositions in classical physics. It's my favorite picture. Most people have seen it a dozen times, I guess. So in classical physics, you have the following. You have state space. quantity is represented by a function from the state space to the real numbers. So A is quantity in the system, let's say energy or position or whatever you like, and it gets represented by a function fa. We assume that these functions are not entirely arbitrary, they are measurable at least. There are other applications where you would have continuous functions or smooth functions, depending on what you want to do, but the biggest class obviously are measurable functions, so let's stay with this. Fa is I didn't make a break, I realized. I'll finish very soon. Probably I'll not define the spectral presheaf today. Maybe I'll define it and talk a bit more about it next time. So again, this is physics, this is pre-mathematics, this is the representation, mathematical representation of a physical quantity in classical physics. Now what about propositions? Let's pick some subset delta of the real line here, just as we did before, and then we can take the inverse image of delta under such a function. So let's just do it, take the inverse image of delta. This will give us a certain subset of, well, certain subset of the state space. And this subset is a representative of A's and delta in classical physics. Why is this a good idea? So this subset state, well, the points of S obviously are the states of a classical system. So if a state S in here, and the function fa will take this to some value in delta. So in this state S, the proposition is true, because A has a value in delta. If you take some S prime outside here, then by definition, fa will take it to some value outside of delta, so your proposition is false. This is why it's a good idea to say this subset here represents the proposition. There is no such easy picture for quantum theory. I didn't talk about, well, as I said, this proposition A has a value of delta, I said it's represented by P. But the big problem with quantum theory, of course, is that you can't just talk about physical quantities having values. And it's not just like in classical physics where you take a point in your state space and this assigns values to all physical quantities by just evaluating the functions at the point. It's just nothing of the same kind happening in quantum theory. That's very much what we try to overcome with this whole scheme. So we want something which in spirit is similar to this. Of course, we don't try to mimic classical theory in all respects. Classical theory is not enough. We want something which allows for the things we have in quantum theory, which are not classical, of course. But this is a nice and easy picture. It's much easier to explain in the quantum picture precisely because it is realist in the sense that in a given state, all physical quantities have values and all propositions have truth values. Okay. So maybe I can define the spectral presheaf. Brief. We will see lots of aspects of the spectral presheaf later on. See its object in a topos. You'll see it has a certain topology. See it's analogous to a classical state space in many respects, and all these things later on. But just for now, we can define it. So we need one thing first. So we start from phenomena algebra. The general assumption is you have a quantum system, and this can be described by a phenomenon algebra of quantities. And more precisely, the self-adjoint operators in the phenomenon algebra will be physical quantities of this system. And if we'll actually do this example next time, it can be very simple. It can be 3x3 matrices on well, a three-dimensional Hilbert space. So it need not be complicated or anything, but let's do the following. Let n be I define what's called the context. Big name for something pretty simple. Is the set of non-trivial Abelian von Neumann subalgebras identity subalgebras of n, of course, and partially order this so I forgot this not b so what's happening here? We take a phenomenon which n, non-abelian in general, and I look at its abelian subalgebras. Not quite all of them. I want that the identity element in each subalgebra is the same as the identity element in the big one. And I exclude the trivial algebra, just the multiples of identity. That's not strictly necessary, but it's useful later on. And then I say, okay, I give a partial order to the bigger subalgebras and smaller ones. And just partially order this. And then we define something following way to each v in the n assign its Gelfand spectrum, and let's call this sigma v. And whenever prime is contained in V, so we have something like a smaller subalgebra contained in a bigger one, then that sigma of I write this for the inclusion of V prime to V. This is a function from the Gelfand spectrum of V to the Gelfand spectrum of V prime. Well, we know the elements here are algebra homomorphisms from V into the complex numbers. V prime is a subalgebra, so it can surely restrict just to the subalgebra. And that's all that's happening. So just take this restriction. And people who know a bit of category theory will see what are defined as functor, contravariant functor. From this category, V of n to, well, okay, actually we have compact Hausdorff space, but we would take this way generally. This just does see them as sets. So this is a contravariant functor from V of n to sets. So, this. Set. just a traditional name for these. They are called pre-sheaves. Pre-sheaf, and then we usually say pre-sheaf over some category just means this is the domain of the functor. So the pre-sheaf over V of n. Okay. At this point, this comes with very little motivation, but we now understand technically what this thing is. There's nothing mysterious, I hope, about technical stuff going on. We can take the phenomenon, look at the Boolean parts, take the full spectrum, plus these functions between them. And I shall stop at this point. This is the central object, and actually we have the convention of underlining objects which are pre-sheaves, so also the components that underline the contravention functor. And so if I just write sigma without any index, it's the whole thing. It's the whole functor, if you like. And this is called